Hello, my name is Emma Slominski, and I am a senior undergraduate student at the University of Utah. I work in the focused ultrasound group here and have been conducting research on simulations of phase correction methods in transcranial MR-guided focused ultrasound. The purpose of these simulations is to study the relationship of acoustic properties to CT values. To do so, we are relating attenuation and speed of sound to Hounsfield units to improve transducer beam focusing. We are also matching simulated temperatures with clinically measured MR temperatures to see if we can match clinical heating in simulations. Two other methods of phase correction are also being simulated to compare how phase correction affects the temperature rise. The three methods of phase correction that are simulated are no correction, clinically determined phases, and time reversal. The clinically determined phases implement the phases used during clinical treatments into the simulation. Time reversal is the third method used that backward propagates from the focal point source back to the transducer to create the phases. The focal spots created by these methods can be seen in the simulated sagittal focal views on the left. For the phases to be put into simulations, the hybrid angular spectrum is used to perform the acoustic simulation. HAS is a rapid full-wave simulation that alternates between propagating in space and the spatial frequency domains. It creates a Q pattern from the acoustic properties based on Hounsfield units. The Q pattern is then input into Penne's bioheat equation to calculate temperatures. We used thermal properties from the ITIS Foundation in Penne's in these thermal calculations. The patient essential tremor clinical data used in these simulations is from the University of Utah. To set up the simulation, the CT first needed to be put into the transducer coordinate system, which was done by registering it to MR from the clinical treatments. Once rotated and translated, the CT is then segmented into 7 different tissue types with respective acoustic values. 3 views of a segmented CT are seen, showing the 7 different tissue types. After segmenting, HAS simulations and thermal simulations follow. Here we have some of our results showing the simulated and experimental hottest voxel temperature rise. The data is for the last 2 sonications for 3 different patients named patient 15, 17, and 23. Time reversal is the yellow line and shows to heat the focus the best, while no correction in the blue shows to be the least based on how little it heats compared to the other methods. Patient 15 and 23 show that the purple clinical MRTI and the orange clinical simulation match well in temperature rise. The cooling for patient 23's MRTI is noticeably slow, and patient 17 does not get as hot as the MRTI compared to the others. The plots shown here each contain the last few sonications from the same 3 different patients as the previous plots. They compare the temperature of the clinical phase simulation to the MRTI temperature at the same time points. The time points are from the first 3 of each sonication. The plots show how well the temperatures are matching during the beginning of a treatment as temperature rises. In conclusion, we found that the method of phase correction can significantly affect the temperature rise. Also, based on the temperature rise seen in the clinical simulation and clinical MRTI, the acoustic values are matching how similar the temperature rose together and the similar peak temperature. We plan to further validate and improve the simulation by using Hounsfield units for attenuation values instead of segmenting into the 7 individual tissue types. In addition, we will also begin performing experiments with ex vivo skulls to compare simulations to experiments. Here are some acknowledgements who have supported this research, and thank you for listening.